So today we're going to study how does the sign of a derivative affect the shape of the graph. Okay. Well, first of all, let's look at the case. Let's look at the following case. Okay, we assume that the function, the derivative function is always positive. Okay. So always positive for x, for all x. Yeah, it's not connected. Okay, so now it's connected. So let's take a look at the function with always positive derivative. Okay. So the interval is going to be like open interval. Okay, now what's going on here? So derivative is positive. Okay, then for any two numbers in this interval, okay, I apply the mean value theorem. Okay, according to the mean value theorem, we have this identity. Okay, and this is positive always, right? So what does that mean? That means f of x2 minus f of x1 is positive. Okay, so that means f of x1 less than f of x2. Okay, so if the derivative is positive, then the value of the function increases as x increases. So in other words, f of x increases as x increases, right? Okay, that means nothing. Okay, so so we can conclude the following. We just give a proof, right? So the positive, it's called first derivative test, or the increasing decreasing test. So this is the yeah, we can. I don't have the name here, but anyway, we use here's the theorem actually. Theorem says that if the derivative is positive, then the function increasing. Okay, if the derivative is negative, then the function decreasing. That's it. Over the interval. So that's important, right? So if you take a look at the function here, f of x equals 2x plus sine x, right? So look at this function. It's hard to draw the graph, okay? And and we find the derivative. It's going to be 2 plus cosine x. 2 plus cosine x. Since cosine x will never be less than -1, so it's greater than or equal to -1. So it's 1. It's positive, right? So the derivative is always positive. That means this implies the function is always increasing. Okay. Now, I know this is a graph, right? Y equals 2x. Okay. So there's a sine x. Sine x added to 2x. So that's a disturb, like a noisy, to the x, right? So actually what you get here is sine x is going to be like that. Okay, it's increasing. Here's y equals 2x plus sine x. My picture is not exactly correct, so it looks like that, doesn't mean exactly like this. Okay, I think when x is between pi and 0 and the pi is positive. Goes like that, okay? So this is a pi. Why it's above the strict line? Because sine x is positive, okay? And this is again 2 pi, okay? Yeah, for x between pi and 2 pi, sine x is negative. So that's the reason 2x plus sine x is smaller than 2x. That's why it's below the strict line. So this is how do we sketch this graph, okay? It's increasing, right? Clearly going up, never go down, okay? So this function, you can even define the so-called inverse function. Let's take a look at the next problem. Okay. So we look at the function x equals just x squared minus 2x plus 3. Okay. This is a quadratic function. I know where it's a function, right? I know the graph, but we don't use the property of a quadratic function. Let's just look at the derivative. So the derivative of function is 2x minus 2, which is 2x minus 1. So this could be positive, could be negative, okay? This could be positive, could be negative. So first of all, let's assume this is 0, right? That implies x equals 1. So 1 divide the interval into 2 parts, x less than 1, x greater than 1. And here's the derivative of the function, okay? Right? So derivative function is 2x minus. So when x less than 1, sorry, greater than 1. When x less than 1, the derivative is going to be negative. When x greater than 1, x minus 1 is positive. So the derivative is positive. Okay? Then you look at the value function. It's quadratic function, it's complicated, but at least for x less than 1, the derivative is negative, so the graph goes down, right? When x greater than 1, the derivative is positive, so the graph goes up. Okay? So if it's parabola, this must be parabola opens upward. Okay? And the vertex will be when x equals 1, right? When x equals 1, the y value is will be 1 minus 2 plus 3. So it's 2, okay? Yeah. You have to use, this is f of 1, right? F of 1 is equal to 2. Okay. So you can sketch this graph right away. So this is a graph. When x equals 1, the y value is 2. And then goes down here, go up there, okay? What is the function, right? Y equals f of x, which is x squared minus 2x. I remember it's plus 3. From the graph, I can tell that there's no zeros for the function, okay? So you cannot find the x-intercept of this graph, okay? If you set the function to 0, b squared minus 4ac is going to be negative, so it's no real solutions. Right? So just for quadratic function, you probably don't need a calculus to study. But you know, for functions of polynomial degrees greater than or equal to 3, this is more useful. Calculus is more useful. Okay, it is going to be yeah. Let's assume that's going to be 1 or 2. Let me check. Plus 6. Let's put 6 here. Six, 6, 6, 6. For some, I'm going to put 14. Yeah. Okay. Doesn't matter. Okay. There's a purpose to doing that. All right. So look at this function. I want to draw the graph. Okay. I want to know where the graph. You know, if I find the derivative, I get critical numbers, right? But I still don't know whether the graph has a local maximum value, local minimum value. It's a function. Unless I know the shape of the graph nearby that point. Okay. If you just want to find the derivative, it's 3x squared minus 15. If this set to be 0, then you get 5, right? So that means x equals plus minus square root of 5. Those are called critical numbers. I know the functions has a local maximum value, local minimum value at some number. That number must be critical number. Now we find the critical numbers. We still have to figure out whether the function has a local maximum value, local minimum value, right? Right? We cannot jump to the conclusion. Sometimes it is critical number, then the function does not have a local maximum, does not have a local minimum value at this point. It's also possible. Okay, so further investigation should be done on the local behavior of the function around those two numbers. Right. So to do that, I have two zeros, right, for the derivative. So you can also express like x squared minus 5, and this can be written as minus x plus square root of 5, right? So we want to know the sign of the derivative. So you have two zeros for the derivative. You can make a chart, okay? And then when is x less than square root of 5, and x between negative square root of 5 or greater less than square root of 5, and x greater than square root of 5, okay? Here's a derivative. Okay. So clearly when x less than negative square root of 5, the first factor would be negative. The second factor also would be negative. So it's going to be positive, negative, negative, positive. When x is between the square root of 5, negative square root of 5, and positive square root of 5, x could be 0. When you plug 0, it's a negative sign, okay? And then similar, it's plus. Then for the function, you can see that this side is increasing, this side decreasing, it's increasing. So the graph looks like that, right? Yeah. So clearly from the graph, before I sketch the graph, I can tell f negative square root of 5 is a local maximum value, right? Right? Look at the picture. This is local maximum, and f square root of 5 is a local minimum value from this. So if I ask you to find a local maximum, local minimum value, you stop here. You don't need to draw the precise graph, but you just find the value, right? So you know the local behavior of the function, and you can clearly this is a local maximum value. So then you have to use the original function. Okay, f negative square root of 5 is going to be negative square root of 5 cubed minus 15 negative square root of 5 and plus 14, right? So let's figure it out. This is a okay. This is going to be 10 square root of 5 plus 14. It's positive number. And f square root of 5 okay, this will be probably negative. It's first of 5 square root of 5 minus 15. You get a negative 10 square root of 5 plus 14. I guess this is going to be negative. Okay, can you tell why it's negative? Because square root of 5 is larger than 2. 2 times 15 is already 30. Negative 30 plus 14 is negative. Okay, so it's negative. Okay. Now, if you really want to draw the graph, you can do that right now. Okay, so this is a negative square root of 5. This is a positive square root of 5. So when x is a negative square root of 5, you get some number here. It's positive, right? And this point will be negative. So the graph looks like that. Okay, and okay, now, so there's two important points you have to mark it if possible. This point and that point, right? And this is a positive square root of 5, and here negative 10 square root of 5 plus 14. This is a negative square root of 5, and 10 square 5 plus 14. And how do you get the y-intercept? Well, y-intercept just let x to be 0. So that's 14. So then there should be one x-intercept here. Okay. And that is going to be what? It's actually is going to be 1. Why? Because if you look at the function, I carefully choose. If I look at this, f of 1 is going to be 1 minus 15 plus 14, it's 0. So that's the reason we have an x-intercept. My question is, can you figure out the other 2 zeros? I think you can. If you only know one factor, you can factor this polynomial, okay? So I know f of x cubed minus 15x plus 14 should be x minus 1, right? Times some quadratic function. How do you get a quadratic function? So if you already know x minus 1 is a fact, because when you plug 1 for x, you get 0. Then you just use a long division. Okay? So you get x, put x squared here, x cubed minus x squared, and you take the difference. You get x squared minus 15x and plus 14. Then you have to put the x here, then x squared minus x, and do subtraction. And then you have to put in minus 14. So again, the minus 14 plus 14, and you get 0, okay? So it's divisible, okay? So that means you get x squared plus x minus 14. Then you can get the other 2 zeros because you know how to solve quadratic equation. Now you can solve the quadratic equation, okay? All right, so this is, you see, we not only find the local maximum and local minimum, we sketch this graph all the way, right? At the same time, we sketch the graph. So let me summarize that. If you have, if we know in advance how does the graph look like, that will avoid making mistakes. This is a polynomial. Polynomial, a quadratic function. The quadratic function, the graph is a parabola, right? Either this or that. Okay, it depends on the sign. Okay, but how about a polynomial of degree 3? Okay, if polynomial degree 3, it also depends on the sign of the leading term. How does the graph look like? I think the graph looks like that if A is positive, and like that if A is negative. Okay, so if you should know how does it look like at the very beginning. Some extreme case may be like that. Extreme case, it's not necessarily it has two local maximum value. Could be like that, right? Also could be like that. Then you do still have a critical numbers, but the function doesn't have a local maximum value, local minimum value. Okay. So the typical case here is y equals x cubed and y equals negative x cubed, right? And this is more general, here is negative. Okay. So, but in general, a polynomial of degree 3, the graph has two special points. One is local maximum point, other one is local minimum point. Okay, and the y value of a local maximum point is called local maximum value. So there is a difference between point and value. Point means a point in the xy plane. Okay, value is just a number. So if I ask you to find the maximum value, you don't need to give me the point. All right. So this is if you know ahead of time, like a quadratic function, you know it's parabola. So when you sketch a graph, that helps you because you know this graph. Okay, if polynomial degree 3, this looks like that. Okay, and how about polynomial of degree 4? It's going to be ax to the 4th plus bx cubed. cx squared dx plus e. And also depends on sign. If a is positive, it looks like that. Okay. Of course, it is possible like that. You know, this is also special. This is, okay. And then in this case, this is a special case. Y equals x to the fourth, right? Okay. And this one will be when the case when a is negative, but it could be also like that. Y equals negative a to the fourth power. Okay. So in general, if you are given polynomial degree 4, the graph has 1. If a is positive, the leading coefficient is positive, then the graph has one local maximum point, 2 local minimum points. Okay? You can see that from the graph. All right, so let's take a look at the graph of the function f of x equals 2x cubed minus 9x squared plus 12x minus 3. So before you sketch the graph, you already know how does the graph look like. The graph looks like that. Right? If you know that, then all you just need to find the critical numbers. You find the critical numbers, find the critical the value of the critical numbers, you get to the point, local maximum point, local minimum point. Then you sketch the graph. All right? You don't need to even make the chart to determine the sign because I guarantee it. Okay? This looks like that. So a equals 2 is positive. So let's find the derivative. The derivative is 6x squared minus 18x plus 12. Let's take 6x out. Okay. So that is going to be 6x minus 2, x minus 1. I know when it's 0, x equals 1, x equals 2. I think if you know the shape of the graph already, there's no need to check the sign of the derivative. Okay? All you have to do is just look at the when x equals 1, y equals f of 1. That's 2 minus 9 plus 12 minus 3. Let's see what do we get. I think it's the value of 2. 12 minus 9 is 3, 3 minus 3 is 0. Okay? When x equals 2, y equals f of 2, that's 2 times 2 cubed minus 9 2 squared plus 12 times 2 minus 3. Okay, and this is a little bit complicated to get. I think this answer will be 1. Let's check. Yeah. So this will be 3 times 2 squared. Right? So you have a 2 cubed. Yeah, combine those two together, 5 2 cubed minus 9 2 squared. Okay, minus 3. Then it will be 10 minus 9 is 1, just 2 squared minus 3, which is 1. Okay, yeah, I can do that. All right, so we got two numbers. Okay, this is if you look at the picture, this should be the local maximum value. Okay, and this should be the local minimum value. And we can sketch this graph right now. Okay, we can sketch this graph. When x equals 1, y equals 2. When x equals 2, y equals 1. So the graph looks like Right, what we can get from this graph, and you see, this is y-intercept. This y-intercept is, oops. Yeah, this y-intercept, this is y-intercept. How do you find the y? Well, it's easy to find the y-intercept. Just let x to be 0. Plug into there, right? So the y-intercept will be 0, right? And this will be -3. Okay. And from this picture, I can tell there's only one x-intercept, but it's not easy to find the x-intercept. It's between 0 and 1. Right? From the graph, you can tell that, right? And yes, we can determine that using the table chart. If you forgot the shape of the polynomial, the graph of a polynomial degree 3, okay, then you have to do like this, okay. So remember the derivative, yeah, 1, 2, right? X less than 1, x between 1 and 2, x greater than 2, and this is a derivative. So derivative is going to be 6 x minus 1, x minus 2. We can check, right? So when x is less than 1, it's positive. When x is between 1 and 2, x minus 1 is positive, x minus 2 is negative. It's negative. When x is greater than 2, it's positive. So the graph goes up, down, and up. You can also verify the shape of the graph using this. Okay? So here's the function. Okay? So the sign of the derivative determines which way the graph go. Could be, it could be decreasing, could be increasing. Okay, so that also gives you the information that it looks like this. But we did not use that. We didn't waste the time to check that, just because we know the general shape of the graph of polynomial degree 3. Okay. We want to know more information about the graph, because when the graph increases, when the function increasing, that's increasing in two different ways. Okay, this could be also increasing, right? That's also increasing. Okay, and in this case, we can call concave down, and here concave up. So additional information we needed to get more precise picture about the graph. Okay, so if the graph is increasing, that should increase in two different ways. Okay, concave down, concave up. So how to determine whether the graph is concave down or whether the graph is concave up? Okay, this is called a concavity change test. Okay, here's a theorem. Okay. The first case, if the second derivative is a positive, okay, then the first derivative is increasing, right? Then f is concave up. Okay. Why it's concave up? Because f prime increasing means the tangent line, the slope of tangent line increasing. The slope of tangent line increasing must be goes like that, right? You see, the slope of tangent line increasing. So that's why it must concave up. Okay, so this means slope, the slope of tangent lines increases. Okay. Right. Second, if the second derivative is negative, then f prime is decreasing, then the graph concave down. Okay. A typical example is the following. This is always my example. You look at x squared. Okay. If you look at x squared, you see that the graph looks like, how does the graph look like, right? This is the graph, right? And then the second derivative is going to be 2. It's always positive. So if you forgot the relationship between the correspondence between the sign of the second derivative and concavity of the function, just look at this function. Okay, this is a concave up, and you look at second derivative, oh, it's positive. Okay, and if you look at the next one, negative x squared, and the graph goes like that. It's concave down, and then the second derivative will be negative 2. It's less than 0. Okay, concave down, concave up. Okay, concave down. Right. So we're back to the function, the polynomial of degree 3. Okay, let's go back to here. So we look at this graph. Okay, look at this graph. Yeah, let me redraw the graph. Okay. So here's a function. 2x cubed minus 9x squared plus 12x minus 3, right? We schedule the graph as follows. When x equals 1, yeah, it goes 2. When x equals 2, it's 1. It's going to be like that, right? Remember this. And how about the concavity of this function? It's clear to me. It's not surprised if the graph concave up here, right? Concave up, right? Then I get another picture. Concave down. So there's somewhere there's concavity changes. Okay? And that point is called the inflection point. Yeah, at this point. And this point is called inflection point. Okay? So for this graph, I guess there's one inflection point across which the graph concavity changes. Okay, let's do it. Let's look at this. Okay, we figured out we have to find out where it is. Okay, we look at second derivative, right? The first derivative is going to be 6x squared minus 18x plus 12. I already take x 6 out. All right. So the second derivative is going to be 2x minus 3. Okay. If you set this to be 0, x equals 3/2, which is 1.5. It's between 1 and 2. So clearly, the second derivative is positive if x is greater than 3/2. That means concave up, right? And the second derivative will be negative if x is less than 3/2, and over that interval, it is concave down. So we determine the sign of the second derivative, and I think where the second derivative is 0 gives you the inflection point in this case. Okay. First of all, what's the definition of inflection? Inflection point is the point across which the concavity changes. Okay. So we find out on the left-hand side, right-hand side, the second derivative is positive. Second derivative positive means the first derivative increasing, means the graph concave up. On the left-hand side, the second derivative is negative. Okay, and so the graph is concave down. So what's the point of the inflection point? The inflection point, we have to find out the value of the function when x equals 3/2. Y value, you have to do the calculation. Okay, it's going to be 2 times 3/2 cubed minus 9 3/2 square plus 12 3/2 minus 3. Okay, you have to simplify it, and yeah, just simplify, right? Yeah. Okay, let's do step by step to simplify. So I got 3 cubed over 2 square minus 9 times 3 square, 2 square, plus this is a 6, 18 minus 3, 15. Okay. Then I have to do subtraction. I have a 3 square out, 3 to get the integer here. Okay, so you take 3 square out. You can write 9 is a 3 times 3 square, so 3 times 9 is a 3 square, so 3 times 3. Then 1 minus, it's going to be -2 square. Okay, so I got -27 over 2 plus 15. So finally, I get 3/2. Okay, this is correct answer, 3/2. So you get the coordinates of the inflection point. Okay. Then you sketch the graph, right? You get perfect graph, you know where is the inflection point, and the concave down, concave up. Okay, when left side concave down, the right hand side concave up. So for polynomials, you should know the shape of the graph before you sketch. Quadratic function, it's parabola, right? Now let's look at another type of function. You will see this kind of functions very often on the test. Okay. So the power of the x is a fraction. Okay. How do we sketch the graph? It's not differentiable everywhere, but the function defines the whole line. Okay, f is defined on the whole line. Okay, might not be differentiable somewhere. I think it's not differentiable at x equals 0, at x equals, yeah, but not differentiable at x equals 0 and x equals 6. Right? How do we sketch the graph? I want to sketch the graph without find the derivative first. That's very important. Yeah. Sketch the graph without finding derivatives. How do you do that? Well, clearly there are some points here, right? X equals 0, x equals 6. So when x equals 0, y is also 0. When x equals 6, y equals f of 6 is 0. So the graph passing through those 2 points or touch these 2 points, right? Then I want to see whether the function is positive or negative. So I'm going to, without the derivative, okay, how much we can get. Okay, x is less than 0, x greater than 0, less than 6, x greater than 6. I want to know the sign of the derivative. Okay, when x is negative, I think the first factor will be positive because the square. You see, x to the 2/3 is going to be x to the 1/3 square. It's always positive. Okay, no matter what is x is negative or positive, so it's positive. Then x minus a negative number is positive. It's positive. When x is between 0 and 6, I think it's still positive. When x is greater than 6, it's negative. How does the graph look like? When x is negative, it's positive. When x is between 0 and 6, positive. When x is greater than 6, like that. Okay? So you get a rough idea about the graph. You still have to tell where the graph is increasing, where the graph is decreasing, right? Well, is there any inflection point? I don't think there's any inflection points here because look at the graph. I think the piece on the left-hand side is concave down. The piece is in the middle is concave down. Piece on the right-hand side is also concave down. I strongly believe the derivative of the function, second derivative function is always negative. Okay. How about the first derivative? Here. So there will be one critical number. Okay. So let's find the derivative. If we find a derivative, right, the function is differentiable on any of the 3 intervals. That's the 3 intervals from, you see. So when you solve the equation, right, the equation becomes a little bit complicated. But if you know ahead of time, you will get one solution here between 0 and 6. Then that will avoid making mistakes. If at least you should know there's mistakes there if you don't get that number. Okay, it's going to be by the product rule. Okay, plus x to 2/3. Okay, and there is a negative sign. So question is, how can I find the zeros? How can you find the zeros? Well, you simplify it. Get rid of 3, right? Right? First we get rid of 3. Okay, just write. It's minus here. Then I don't like x to the negative power, so I multiply by x to the 1/3. I also multiply 6 and 2/3, right? And then the first term be 2 x to the negative 1/3 times x to the positive 1/3 is going to be x to the 0. That is 1. Then combine the other two, it's going to be 1, right? Minus x. That's 0. So you will get 12 minus 3x minus x equals 0. It's minus 2x. Okay. So you will get x equals 4. Yeah, x minus. Okay. X equals 4 is between 0 and 6. Wonderful. So we got it. Okay. So the function, if you look at the picture, I don't need to even determine the sign of the derivative. I can tell that we have a two local. I know f of 0 equals f of 6 equals 0. This is the absolute minimum value of the function, okay? From the graph. And f of 4 is the local maximum value. Did I check the sign of the derivative? No. I sketched the graph before even I find the derivative. You should learn that, okay? Then that will help you to avoid mistakes, making mistakes. From the graph also, I can tell that, yeah, let me check what is f of 4, right? F of 4 is 4 to the 2 over 3, and 6 minus 4 to the 1/3. Oh, let me check what's going on here. 3 over 2. Yeah. So what I have to do? We look at the picture again. We look at the picture again. It looks like that, right? And we got the local maximum value of the function. I believe that there's no points of inflection. Okay, always concave down. I can, yeah. The derivative. So derivative the second derivative of the function should be always negative. You can check that. Can you find the second derivative? Yeah, let's take a look at the second derivative. Right? X equals x We find the first derivative. Yeah, it's a little bit complicated. Okay. We have to differentiate. Wow, it's complicated, right? In order to determine the inflection point, or in order to prove there's no inflection point, you have to look at the second derivative of the function. Okay, let's do this. By the product rule. This is a product, right? And negative ones, I have this. And then minus 2/9 x to the negative 1/3. And this also would be negative. 2/9 x to the 2/3. 6 minus x, 5/3. You have a negative sign, you put it outside. So that's it. So all the terms are negative. Okay, for at least between 0 and the 6, right? Can we prove this? We have a 2/9. Let's take a 2/9 out. I take the term with the least power out. I also take 6 minus x to the negative 5/3. Okay, I'm going to collect all the terms here. I think we get square here. Okay. Then plus x, 6 minus x. Okay. Then also have I think that's it. Okay. If my computation is correct, I get 36 minus 12x plus x squared plus 6x minus x squared plus 6x minus x squared plus x squared. So x squared all gone. 36, 12, 6x, 12x gone. So what I get is going to be 8. 36 divided by 9 is 4. 4 times 2 is going to be 8. All right. So we get this. Now we have to check the sign of this each interval. Okay. So what is our interval? Okay. So this is the chart. X less than 0, x greater than 0, less than 6, and x greater than 6, right? The second derivative is going to be negative 8, x to negative 4 over 3, and 6 minus 8 to negative 5 over 2. So when x is negative, this term is always negative. Okay, the term 4 with x to the negative 4 over 3 is always positive. Okay, when x between 0 and 6, 0 and 6, and this is going to be negative. When x is greater than 6, I think this is positive. Okay, positive concave down, concave down, concave up. So something's wrong with our picture, right? So think I'll go back to the. So concave down, okay. What I draw at the very beginning, I said, yeah, this is a question mark. I put it there. Why this there? Maybe that we make mistakes at the very beginning. Yeah. Okay. Oh, we said negative, right? I already said negative. But when I draw the graph, I did not draw the graph below the x-axis. Okay. So be careful about the graph. So the graph should go below that. Okay. Below the axis. Oops. Yeah, it goes. So now we get the inflection point. Okay. We see that between negative and 0, its second derivative is negative concave down, and between 0 and 6, it's also concave down. But between when x is greater than 6, it's concave up. Okay. So this is the inflection point. Yeah, let's go back to the picture. Okay, so this is the inflection point. And here's the second derivative is positive, concave up. Here's second derivative is negative. The second derivative is negative, concave down, concave down. Okay, so you get an inflection point. That's the picture. Step 1, you just draw the graph without using as a derivatives, because it's easy to make a computation mistakes. So just like show you, see how many of you can easily handle those factors with negative powers, fractions, right? Fraction powers. It's not easy. Okay. So if you draw the graph before you find the derivative, before you simplify, then you can make a correction. Okay. Even that, I'm making mistakes. I did not pay attention to the sign. So you see, this should be negative, right? Negative. Yeah, negative. So the graph is below the axis. Nobody point out. I draw the graph. Okay. And so we get perfect graph, right? There's only one fraction. There's only one inflection point. Okay. Okay. Yes. The last one? This one? No, this is a x greater than 6. The second derivative is positive. The first one, it's negative. Yeah, that's what concave down, concave down. Okay. I said that's easy to make mistakes for the sign. Okay, so if you know ahead of time, how does the graph look like? that helps you to find out the computation mistakes. Okay. All right, so let's take a look at the next one. Let's look at square root of x, 4 minus x. Okay, it's a very similar problem. Now this time, it's slightly different. X cannot be negative. Okay, so you look at the graph. I think look at the sign, right? First of all, x is greater than 0, but when x equals 4, it's going to be 0. So you look at the picture here, x is greater than or equal to 0, right? Or x, yeah. We should write x is less than or equal to 0. Yeah, 0 should be less than or equal to x. X is greater than. Okay, so here's the function. So for x between 0 and 4, right, it's positive. And for x greater than 4, it's negative. So you can easily sketch the graph. When x between 0 and 4, it's positive. When x is greater than 4, it's negative, right? So clearly the function has a one absolute maximum value. But there's also local minimum value. Why? At the end point. Okay. It's possible the concavity changes somewhere. So maybe it has inflection point. Okay. It looks like, you know, one side this concave down and another piece concave up. So we have to find the second derivative, first derivative. Okay. So let's find. We already sketched the graph, right? But from the graph you can get some information. So the second derivative, when I don't want to use a product rule. Okay, this is a function is 4x to the 1/2 minus x to the 3/2, right? So I get 4 times 1/2 x to the negative 1/2 minus 3/2 x to the 1/2. Okay, I should be able to get one critical number between 0 and 4. Can I? Yeah, let's look at. Set this to be 0, right? It's a strange equation, but we can do that. Okay, so you multiply both sides by x to the 1/2. What do you get? You will get, yeah, also multiply 2, so 2 cancels out. That's 4 minus 3x equals 0. Okay, x equals 4/3. Yes, it is between 0 and 4. It's a critical number. And this critical number, you don't need to know the sign on the left side, right hand side. And clearly, f of 4/3 is the absolute maximum value, because from the graph I can tell you. Okay. can calculate that. So how do you calculate? F of 4 over 3 is going to be square root of 4 over 3 and 4 minus 4 over 3. Okay, so this is going to be square root of 3 over 2, and that is going to be 3. You take a 4 out, and I think it's 2 here. Okay, it's a number. Okay, it's not a perfect number, but it's a good number, right? 16 3 of squares. Okay, it's a number. Okay, this is our absolute maximum value. So what else we should do? We already know the intersection point, right? We have to find a second derivative, determine if there's any inflection point. Okay, the second derivative of the function would be negative 4 times 1/2. Okay, this time I'm going to take negative quart out. Also take x to the negative 3 over 2 out. So I get a 4. Plus x. Okay. Yeah, be careful with the sign. It looks like it's always positive for x greater than 0, negative for x greater than or equal 0. For x greater than 0. So the second derivative is negative, means always concave down. It's always concave down. So that means f of x is concave down on the interval from 0 to infinity. Okay. Yeah. So when you draw the graph, just be careful. It goes like that, I guess. Okay, we double check. Let's see. Yeah, so this is always negative. It's not like, I thought it's going concave down, then concave up. It looks like that, right? But it's not. Okay, just always concave down. And that's possible. Okay, it's possible. And this is the maximum absolute value. Yeah, here's 4 over 3, and f of 4 over 3 is the highest point on the graph. Okay, and there's a the derivative. Yeah, second derivative always negative over this interval, and here the first derivative is positive. And here the first derivative is negative. It's going down. So this is a graph. All right, so let's go over this problem quickly. So if you are given function like that, okay, what is first thing you have to do? Sketch the graph without finding the derivative. Do your best to do that, right? at least you can tell where's the zeros, which part is above the x-axis, which part is below the x-axis, right? Okay, then I get a graph like that. Then if we look at the graph, the function must have a local maximum value somewhere between 0 and 4. Then you go ahead to find the derivative and solve the equation. Now, if you don't get the number between 0 and 4, something's wrong in your computation. Okay? So this helps you to avoid making mistakes if you know the graph ahead of time. Sketch the graph, not precise, right? Because you really have to find the y value of the highest point. So in order to plot the graph, draw the graph. Okay. So then you find the first derivative of the function. Okay. Then you find the critical number, and my computation is okay here. I get a 4/3. I'm pretty sure this is between 0 and 4, and it's okay, right? If I get a negative number, something's wrong. Okay. So the rest of the part of the computation just gives you the precise data where is the local maximum point or absolute maximum point. Okay. You get the exact information. Okay. So yeah, you have to pay attention when you do exercise.